Okay, so last time we discussed Kummer's exact sequence. So we have some integer n, and then so we proved that the sequence of sheaves, let me write it this, okay, Gm underlined goes to Gm underlined. So this is just the sheaf of invertible function, and this map takes a function to its nth power. And this is the kernel. And we proved that this sequence is exact in the category of sheaves on the big étale side on Z over Z is n inverse adjoint. Весь детально получше. Yes, yes.
In the previous theorem, we had a theorem on cohomology of quasi-coherent sheaves in the category of OX modules.
Right.
So if we compute cohomology of quasi-coherent sheaf as an abelian sheaf,
It will be the same. It will be the same, though it's not. The proof is sort of similar to the case of the risky topology. So how you prove that homology of O module is the same as homology of the underlying sheaf of abelian groups. You use the notion of Fleby sheaf. So you check that if your O module is injective, then it's Fleby. And there is a similar argument here. Okay? So is exact. So it's exact on this big étale side. And in particular, I can restrict this sequence of sheaves on the biggest étale side to any scheme X over over Z with n inverse adjoint. So so suppose I have a scheme over spec Z in inverse. Then we have sequence. This time I will call it just invertible functions. That's the same sheaf, just restricted to the small étale side of X. That's notation for this sheaf. Yes, exact in sheaves X étale. Okay. So just a notation. So this sheaf, mu n. So I recall that by definition, its section on any U is the group of invertible functions on U whose nth power is equal to 1. And it's then another notation for this sheaf is Z mod n twisted by 1. So let's note that, well, in general, this sheaf is not constant. But if say epsilon in as a global, well, if this ring has a primitive root, nth root of 1, if we fix it, so if this is a primitive f root of 1, then the map that from the constant sheaf to this twist that takes 1 to epsilon is an isomorphism, right? So, so for example, for schemes over algebraically closed field of characteristic relatively prime to n, this is just a constant sheaf. Нет, ну, как бы я бы сказал, что а как его еще обозначить? Ну, он очень похож на постоянный пучок, но вот не совсем. Собственно,
раньше была нотация от единицы, мы подкручивали на обратимый пучок.
Да, это не имеет значения, это не имеет отношения.
Нет, ну там тогда можно писать миллиард в тензорной степени, кому хочется.
Ну да.
Но мне даже, наверное, больше нравится.
Ага. То есть я бы сказал, что первое место, где вот это обозначение появляется в математике, это вот здесь. Okay, so why this is useful? Well, so any short exact sequence of sheaves gives rise to a long exact sequence of cohomology groups. So let's see how what we can derive from this. So we have one. We have h0 of x with this z mod and z of 1 coefficients. So these are just roots of, well, invertible functions whose nth power is equal to 1. So if x is connected, say, over algebraically closed field, then it's just z mod and z, as we discussed. So then we have global invertible functions. Let me just write it as x or star x of x. Then we have nth power map. Then we have this group. And then we have the first étale cohomology, of x with coefficients in O star. And now, so I recall that this classifies torsors over this, GM torsors in this case, right? And we proved that, more generally, we proved that GLN torsors for faithfully flat topology and in particular for étale topology are all locally trivial for the risky topology, that's the same as torsors in the risky topology. And we actually proved that these are line bundles, right? So this is Picard group of x. Now we have nth power map. to again to Picard group. Значит, мы доказали, что GLN-торсеры на X это то же самое, что векторное рассвоение ранга n. В частности, GM-торсеры это то же самое, что линейное рассвоение. Это нетривиальное было утверждение, следовало из плоского спуска. Вот. То есть вот эта группа, она совпадает также с топологией Зарисского. X со звездочкой. Вот. Then the next map is to let's see to H2 et al. Of X with coefficients in Z mod and Z twisted by 1, and then the sequence there continues. So this map has a special name. It's called the first Chern class map. So it's from Picard group to second et al. Homology, this time with Z mod and Z coefficients. But I can take any n, provided that it's invertible in the ring of global functions on X. Okay? So this is first Chern class. Okay. So, for example, let's consider, let X be a curve, smooth, proper curve over, let's say, over an algebraically closed field. So let's see what we can say from this short exact sequence. So we have well, we have mu n of k. So this is just the group of nth root of unity here. Here we have k star. Then we have k star. This is nth power map. Then we have Picard group of X. This is multiplication by n to the Picard group. And then we have, I missed something, yeah, sorry. I should have put here H1 et al. Of X with Z mod and Z coefficients twisted by 1. And again, this is a constant sheaf in this case, but non-canonically, so it depends on the choice of root of unity. So this is peak X. And then we have H2, and so on. So Z mod n twisted by 1. So now, in particular, it follows that. So what is the Picard group? Let's say. So what we conclude, for example, from this is that H1 et al. Of X with coefficients in Z mod and Z twisted by 1 is the kernel of this map. So this is peak X, and this is my notation that I'm going to use. This is n torsion points here. So this is the kernel of multiplication by n. And we already discussed that the structure of the Picard group of a curve. Well, this is this is the set of k points of the Picard scheme of x. And the Picard scheme of x has the following. It's a group scheme, which is product of z. You have degree map, right? And an abelian variety, pick 0. So this abelian variety has, let's say, G is the genus. So, so we have genus of x, and pick x has the following structure. It's a group scheme that has connected component, pick 0, and the quotient is z. And over an algebraically closed field, this always splits, right? You can construct a line bundle of degree 1. And again, the key point here is that this is an abelian variety of dimension g. So pick x is an abelian variety. So, and here we are looking at n torsion points in this abelian variety. And, well, multiplication by n provided that characteristic of my field, right? I still assume that characteristic of k is relatively prime to n. So this map, pick x to pick x, which is given by multiplication by n. Well, it's an Étale map, right? Its differential is just multiplication by n. And it's known that its degree, this is true in any characteristic, is equal to n to 2g. So this has degree of degree n to 2g. So that means that the kernel of this map is a group of this order. And, well, in fact, for a abelian variety, again, over a field of characteristic coprime to n, it's known that this group is isomorphic to z mod n z to the power 2g. And this follows if n is prime, it's thematic. So, so this implies that pick x n is isomorphic to z mod n z to the power 2g. Right? So I just explained that the kernel is an abelian group of this size, right? So if n is prime, and it's also killed by every element in the kernel is killed by n. So if n is prime, I have only one choice. But if n is not prime, you can use induction to prove that there is only one choice for this. Okay? So, is it okay? Ну, смотри, значит, я утверждаю, что из вот этих двух обстоятельств, а именно обстоятельства какие? Что это отображение степени вот такой вот степени, и что оно Étale. Что это означает? Что слой над нулем состоит из, над алгебраически замкнутым полем. Это группа ну, он приведен, поскольку отображение тально. И ну, геометрический слой, ну, слой над алгебраически замкнутым полем, состоит из вот такого количества точек. Поэтому я знаю про слой, что это группа, которая убивается умножением на n, и которая значит, имеет вот такой порядок. Если n простое, то отсюда немедленно следует, что эта группа абстрактно изоморфна вот этому. Но я утверждаю, что это также следует, если n любое. Ну, например, как доказать это, когда n — это степень, квадрат простого числа? Все, что нужно знать, это что умножение на p — сурекция. То есть у вас есть... Да, надо разложить умножение на p в квадрате в композицию двух умножений на p и воспользоваться тем, что на пикаре, поскольку это отображение групповых схем и дифференциал не нулевой, это значит, что образ открыт. Значит, поскольку это подгруппа, значит, он и замкнут. Ну, это не очевидно. Это не очевидно. В общем, надо смотреть книжки Мамфорта. Это не так просто доказать. Вот.
Это делается с помощью самопересечения обильного линейного расслоения. Но нужно написать формулу, как умножение на n действует на максимальной степени пересечения. Вот. И тогда коэффициент КТ в степени отражения.
Да. Very good. So, but there is another way actually to derive this. Namely, let's recall that homology of any connected scheme, first homology of X with coefficients in Z mod n, well, I do not put twist here, so over algebraically closed field, again, these two shifts are isomorphic, so homology are the same. But we proved all this classifies Z mod and Z torsors over X. And we can use this theory of fundamental group to classify Z mod and Z torsors, right? These are covers whose automorphism group is Z mod and Z. So this is homomorphisms from the Picard group, from the pi 1 of X, pick some base point, to Z mod and Z, right? And so we have done a lot of work computing this group in particular for smooth proper curves, right? So if the base field has characteristic 0, then this group is just pro-finite completion of the topological fundamental group. So in particular, it's we know that homomorphism from this group to Z mod and Z, these are the same as homomorphism from the topological fundamental group to Z mod and Z. And that's by classical computation of the fundamental group of Riemann surface is this, right? So the abelianization of this group is free group of this rank. And if base field has characteristic P, we still know this. Because what the main theorem that we proved was that the maximal pro-P co-prime to P quotient of this group is the same as the maximal pro-P quotient, co-prime to P quotient of the pro-finite completion of the topological fundamental group. So I will say, I will write it. So characteristic of K equal to P So what we proved is that there is a map which goes in this direction, pi1 of topological of surface of genus G. So we know what this is. And here I have pi1 etal of, this is etal, of x. So we have this map, and this is in factors through pro-finite completion, and introduces isomorphism. This is isomorphism by our specialization theorem on coprime 2p quotients. So here we are interested in homomorphism from this group to Z mod and Z, and then it's coprime 2p. So it's in any characteristic, it's just homomorphism from this group. Okay? So this gives another proof of this fact. Good. Now I want to discuss another piece of another general construction. So let's discuss functoriality in for étale sheaves and étale cohomology. So if you have so we need notion of direct and inverse image of sheaves. So functoriality well, so some of this construction works for morphism of sites, but so I will formulate it just for étale site to save time. Let's give a definition. Suppose we have, so let F be a morphism and then and F is say a presheaf on X étale. So I want to first define its direct image. Well, so how to do this? So imagine that I have X, I have Y, and I have an étale open set on Y. So that means that a scheme U together with an étale morphism. And so what is it? U over Y. Well, what you can do, you can take the fiber product. That's the natural construction. That's generalization of the preimage. So you can take X times U over Y. So you have actually a morphism of étale sites. At least of them, I didn't tell you what a morphism of sites is, but everyone knows what a morphism of categories. So the categories of open sets here, there is a functor from the category of open sets here to the category of open sets here, given by this fiber product construction. So and I declare this to be f of x times u over y to y to x. So now, so this this map of entire sites has the following property that if, say, you have a cover so if you have a collection of entire maps over U is a cover, then the collection that is obtained by base change, so I can base change to x or y and map it to U times x over y, is a cover. So the étal and the union of images is everything. And therefore, it's if F is actually a sheaf on X étal, or something, yeah, okay, then this construction, F star of F, is also a sheaf. So this defines the direct image functor on sheaves, which is left exact. Therefore, since we already know that the category of sheaves has enough injectives, you can take its derived functors, higher direct images. We can also construct inverse image. So the functor that we just defined from sheaves on X étal to sheaves on Y étal, F star, has a left adjoint which is exact. Yes, exact. Okay? I will give you a formula for the left adjoint functor. Left adjoint, and I will call it F inverse. So how you define it? Well, definition is, so how you define it for sheaves in classical topology? You first define certain pre-sheaf, then you sheafify it. Here you do the same thing. So first you define it as a pre-sheaf. So so suppose I have an étal open set, and so I need to assign to it an abelian group. What can I do? So I will write the formula. That's limit over the following diagram. So F, first of all, it's F of V map into y. And what is v? What is the diagram that we take a limit over? So I have x and I have y. Here I have u. Here I have u. So in classical topology, if u were a subset of x, you would take limit over all v that contains the image of u, right? So I want to write down a similar condition here. So what would be similar, what would be a natural thing to do? I'm asking because it's easy to give a run. Well, so there are two candidates that you can imagine here. So okay. We are given v over y, and we are taking the limit over all. We are given u over x, and we are taking the limit over all v over y.
Yes, we should have a map from the pullback of v to u.
So one condition would be indeed that the image of u under this composition is contained in the image of v. This is one possibility. This will not give you the left adjoint functor. And the correct thing to do is what Stepa, you suggested, but I will write it down. Well, it's equivalent. So you take the limit over all diagrams of this form. So it's not only that the image of v contains the image of u. You are given a lift, right? That's part of the structure. So why it's important? You can take a limit with taking a limit not over a set, right? Partially ordered set. We are taking a limit over a category. So you should take, well, we consider these diagrams as a category, right? So what does it mean? It means that That's the only difference with classical definition. So you don't have to care about this. And we will see how it, I will kind of give you an example in a second that illustrates the difference, okay? Что? Есть морфизмы. Их как бы, вот если бы я не фиксировал, то их было бы гораздо больше. Потому что представьте себе, что у вас какое-нибудь такое тальное накрытие Y. Тогда, да еще накрытие ГЛОА, скажем. Тогда вся группа ГЛОА бы здесь действовала. Когда я рассматриваю морфизмы, такие вот объекты вместе с таким отображением, их становится меньше. И это важно в конструкции. Это совсем будет другой ответ. Okay? So, and now this is indeed a good exercise. Complete the proof. Complete the proof. So you need to check that junction. And exactness. And now I give you a promised example. Well, it means that it's well. So the functor which is adjoint to another functor is either left or right exact, right? So you can prove exactness this way, or is it?
No, I'm trying to say that. I mean, would be really clear about this description. Can we just say F star preserves limits as by Freud's theorem F equals.
I think we do care about the construction. I'm trying to kind of omit proofs, at least lone proofs, that uses construction which are not to be used later. Okay, yeah, so I haven't finished. So this is a pre-sheaf, and you have to sheafify it. Oh, by the way, let me before I continue, let me I owe you an example. So digression. So someone asked me. So remember that we discussed sheafification last time, and in order to construct sheafification, we defined a functor epsilon from pre-sheaves. That works pre-sheaves on some side C to itself. Well, how it was defined. So if you have epsilon f of u was defined as limit of locally given sections f of u underlined, where u is where the limit is taken over all yes, this limit is taken over all covariant sieves. No, this way. Sorry, sieves. Well, I didn't tell you what are the morphisms. Inverse and direct means that just you can always take the opposite category. So that was the construction, and then the question is, the claim was that epsilon of f need not, well, the claim was that sheafification can be constructed as by applying this functor twice. And someone asked me why we need to apply epsilon twice. What is the simplest example of a pre-sheaf such that epsilon of f is not a sheaf? And here is an example. So example, epsilon of f need not be a sheaf. Be a sheaf. Well, let's take some topological space X. Say R with usual topology. And F is going to be the constant pre-sheaf. So f of u is equal to z for all u. Is it separated? Okay, so what is, so let's compute epsilon of f. What is it? So I claim that the answer is the following, that epsilon f, so we look at the classical topology on R, right? Nothing fancy. But I claim that epsilon f of u is going to be also z for all non-empty u. And epsilon f of empty set is 0. Right? So you may think that this is stupid because you consider something, well, an open set like this, which is disjoint union. And then, well, you have a locally given section, namely 1 here, 2 here. And this does not glue. So this should be a section of epsilon of f, but contrary to what I claimed, that this is just z. But that's not true because the intersection is empty. But our sheaf f has this property that f of u is equal to z for all u, including the empty set. And all the restriction maps are identity maps. So you have a kind of covariance sieve generated. So this is my u, and u is just disjoint union of u1 and u2. But so what are locally? So it defines a sieve. But what are locally given sections? These are just sections here, such that their restriction to the intersection coincide. But this is an empty condition, right? So now, so I think I convinced you that this is true. But why this is true? Why, after applying epsilon, we get empty? We get 0 on the empty set. Yes, because yeah, so we can take for the covariance sieve empty set. It's allowed. So if you remember that this u underlined is a category, right, of open subsets over your u. And if your u is empty, then you can take for the covariance sieve just the kind of category with 0 objects. And then this is going to be 0 by definition. Okay? So now, when you apply this twice, you get locally constant functions. Well, these examples appear in nature. It's not something. Okay, so that's. I hope that I. Now, let's discuss. Let's go back to this construction of the inverse image, and let's discuss a special case of this, a very important special case. So in classical topology, to play with sheaves, it's very convenient to use the notion of a stock. For example, when you check that a sequence of or a complex of sheaves is exact, you check it on stocks. That's not kind of, you don't have a notion of stock for any site, but you do have it for the étal site. And this is very extremely useful. So let's discuss what is a stock of an étal sheaf.
So in particular, the notion of flabby sheaf you alluded to earlier requires stocks.
Flabby means what? I think that it's conditioned that every section of local section over any open set extends to a global section. It doesn't require stocks.
Oh, yeah, it's equivalent to any stock.
Yeah, but I can sort of formulate it in such a way that it's okay. Stocks. Okay, so here is a definition, some terminology. So, well, that's first definition we already see. So, a geometric point of X of a scheme is just a map from the spectrum of an algebraically closed field, of separably closed field to X, where K is separably closed. So I will call this map usually X, small x overlined. And so for any geometric point, you have this is one point, so you can look at its image. Its image is going to be a point, usual point of X, image. So, X bar, geometric point, is said to be algebraic. If so, the following condition holds. So you have if you let's look at the residue field of this point. So then the map from spec K to X gives me a map of on embedding of fields. And the condition is that this is an algebraic extension. So if it's an algebraic extension, then K, it exhibits K as a separable closure of this. So algebraic points, geometric points, are obtained as follows. So you take just a usual point, and then you choose a separable closure of its residue field. This gives you algebraic points. Now, so another definition so when you play with classical topology, we have a notion of a neighborhood of a point. So let's see what a neighborhood in Étale topology is. So definition, in Étale, neighborhood of X is the following diagram. So you have X, you have U, which is Étale. So here you have geometric point. And in addition to that, I want to fix a lift. So again, the feature of this definition, I want to emphasize that it's not only that I require that U, image of U, contains this little x. I want to fix this map. So here is a picture. So you have maybe some x, maybe it's a curve, and then you have a cover. This is U. So this is my U. This is x. You may even assume that the base, that X is over an algebraically closed field, and K is this algebraically closed field. X is defined over. So you have a point X, which is X bar in my case, and then the geometric neighborhood consists of this U together with a marked preimage. So and I have many choices. I might have many choices. So then, we have a notion of a stock of a sheaf. So if I have any sheaf F and a geometric point, then, well, there are two ways to define stocks. Equivalent. So you can just take the inverse image, x inverse, apply the functor that we define there to F. Well, you get a sheaf over the spectrum of the separably closed field, and sheaves over the spectrum of separably closed fields is just abelian groups, right? Because any is determined and its value on spec K. So you don't need to Sheffify it. So that's just a vector. That's just an abelian group. Think of this as an abelian group. Or kind of phrasing definition in this special case, we can line down a formula for this. So this is a limit over all neighborhoods, over the category of neighborhoods. Of X. So neighborhoods, again, it's not a set. They form a category. And we take limit over all f of u. That's just a reformulation of the definition that I gave over there. Now, let's assume that my point, geometric point, is algebraic. So assume that this bar is algebraic. So you have then the residue field of its image, and this is K, and this is separable closure. Then so I claim that the stock carries a natural action of the Galois group. Galois group of K over this. Galois group of algebraic closure of this field, separable closure and algebraic closure, Galois groups are the same. Let's see why. So I claim that Galois group acts on this category. So if you have an étale neighborhood, so it consists of U mapping to X together with this lift. But I can modify the lift by using the Galois action. I can compose this map with Galois action, right? Pre-compose it. First, I go to spec capital K to spec capital K using an element of the Galois group, and then I apply that map. So, as you see, we are taking the limit here over a category which is equipped with action of the group. And so these guys this is an equivariant functor from this category to abelian groups, right? F of u does not change this f of my object of neighborhood does not change if I modify this, right? That means that I get an action of the Galois group here. So maybe I should, at least for me, it took some time to understand what it really means. So let me convince you that this is indeed true. So, so suppose you have an element, sigma, in the Galois group. And I want to tell you how it acts on elements of this limit. So, so what is an element of this limit? That's a collection that assigns to every, and I need some name here, to any neighborhood pair u x tilde an element in this group u x tilde, right? So this is my notation for a typical element in this limit. For every u and x tilde, I have some element here. So let's see how we can use an element of the Galois group to modify it. Well, that will be the following. So we have
this is direct limit, not inverse limit, right?
direct limit, right?
So an element of that is an
So,
class of pairs. And a section of that.
right. So you're absolutely right. So kind of an element in this limit is given by an étale neighborhood and is given by an étale neighborhood and section S, right? Yeah, maybe, okay. So I think of this as, okay. So here is my action, S, U, now I take sigma composed with x tilde, right? So it looks very stupid. So first of all, why it makes sense? So an element in this direct limit, as Stepan said, so it's given by the following. So you fix an étale neighborhood, and then you fix an element here. So I have an étale neighborhood, and S is an element of f of u. F of u. Now, what I do here, I choose another étale neighborhood. And for this étale neighborhood, I also have to fix an element in the corresponding value of f. But u is the same. Since my neighborhood is different, right? Because x tilde is different. But f of u, but the value of my functor on this neighborhood is still the same. The point changes. Well, which point?
X.
No, x tilde changes, but this point does not change. Because the Galois group,
Right, because we don't
Yeah.
have any like commutativity. Right?
because sigma acts trivially here. Does it make sense? Okay. So here is another way of thinking about this construction, which is very, very important. The corresponding field extension must be separable. No, I do not require this. So as I said, so they only, yeah, you're absolutely right. So if my I said incorrectly. So algebraic points are not in one-to-one corresponding. Well, I said that algebraic points are obtained in the following way. You take a point of x, and then you take separable closure of k of x. This is an example of algebraic point. But you can take any field which is in between the separable closure and algebraic closure. That will also work. So I do not require, I only require that this is an algebraic extension. I do not require it to be separable. So if k of x is not perfect, then there is a difference, right? It's, so this is kind of, it sits in here in k of x closure, and it contains the perfect closure, the separable closure, right? So this k must be in between these two. For example, let's consider the following. Let's give another interpretation of this. So suppose I have x and x, and I have spec k. This will be my geometric point. And by definition, it factors through the residue field. And that's my x. So, and let's give a name to this map. Let's call it pi. Then pi x bar inverse of f, which is the stock, can be computed in two ways. You first pull it back here. You get a sheaf on the spectrum of a field. And then you apply pi inverse. Now, we already discussed that the category of sheaves, sheaves of abelian groups on spec k of x with a Tal topology is equivalent to the category of continuous representations of the Galois group. Continuous of Galois group of k over k of x. So, in fact, this equivalence here is given by pi inverse functor. So in the case when, so you can think of this pi as a geometric point here, algebraic geometric point. And so the stalk, if you have a sheaf on spec k of x, its stalk at this geometric point is an abelian group. And well, there are sort of many ways to see that it has a Galois group action. There are two ways to see it. Either using this construction, right? Or just by observing that what is a sheaf? It's in particular, it's a presheaf, right? So it's a functor from the category of covers to the category of abelian groups. And this guy has many automorphisms, namely the Galois group. So this gives you an action of the Galois group here.
And this identification of categories is not canonical.
Well, it's canonical once you choose any algebraic geometric point. So you can take so there is you need to choose any field which is in between these two. For example, you may choose algebraic closure or separable closure.
We can't choose any field because otherwise Galois group will not exist.
What do you mean?
Galois group is only defined for separate groups.
Why? You can always define it as a automorphic group, right? Yeah, it will be the same for the separable closure. So yeah, it doesn't matter. So what is really important is the choice of the separable closure. It doesn't. Nothing will change here if you replace your k by if you vary your k here in between. It will be the same functors.
If C over Q, this will be false. Yes.
Well, this is not an algebraic. This is not an algebraic point. Yeah, that's as important. So Galois group, we consider only Galois. We use this only for algebraic extensions.
So can we just say that by definition this Galois group is the Galois group of the maximal separable extension?
Yes, that's true. That will be correct. Okay. So kind of reinterpreting that construction, you can reinterpret it as follows. So take an algebraic geometric point, take the underlying usual point, and consider the inverse image functor to this point, and identify the category of sheaves here with the category of Galois representations. By the way, what does it mean that the Galois representation is continuous? It means the stabilizer of every element is open. So this way, we obtain so any diagram like this gives me a functor from the category of sheaves to the category to this category. That's the construction that I explained over there. Good. So yeah. So let's see what I. Here is another interesting example of the stalk. So let's fix an algebraic point. Point of x. So again, so I have spec k x, and I will assume this time that with K equal to separable closure for concreteness. So let's assume that this extension is not only algebraic but also separable. So let's apply the construction of the stalk to the structure sheaf. So here is my name for this, so strict generalization, and this is the stalk of the structure sheaf at x bar. So what we do here, so we take the following category. We consider all neighborhoods.
Wait, what does SH stand for?
So this stands for the strict Henselization. So what we are doing here? So we are taking. So what is written here? That's definition, right? And I define strict Henselization as the stalk of this sheaf. So what it means is that you take the limit, the inductive limit, over all étale neighborhoods. So, and you take the limit of functions on U. So suppose we, for a second, we replace étale topology for the Zariski topology. What will we get? Let's take the limit, the same thing, but now we take for this just a point of x, and we take the limit over all étale, for all open subsets that contain this point. That's the definition of the stalk of the local ring, or x comma x. And what we have here is an analog, right? When we play with in algebra, with kind of with schemes and with classical Zariski topology, it's very important to it's important too to consider these local rings, localization of the structure sheaf at point x. And this is an analog. So it's it plays the strict Henselian rings play the role of local rings in étale topology. And I will finish with a definition. We'll talk about this more next time. So. So this is a ring, and this ring is local, right? But it has even stronger property than locality. So definition: a local ring. A, comma M. M is a maximal ideal. Is called Henselian. If the following holds, for all monic polynomial f of t is coefficients in a of t, is coefficients in a, and every simple root alpha that's in A mod maximal ideal, I will call it K, such that f of alpha is 0. So I take my polynomial with coefficients in A, I reduce it modulo the maximal ideal, And I assume that this root is simple. F bar prime of alpha is not 0. There exists alpha tilde in A with two properties, that f of alpha tilde is 0 and alpha tilde is equal to alpha modulo m. Okay? And A is strictly Genselian if the residue field, if A modulo M is separably closed or algebraically closed, is separably closed. So what are examples of this? Two examples, and I have to stop. So one example is ZP, right? And that's this is Genselian by Hensel lemma, if you have, right? And that explains the name. So another example, well, it requires a little bit of argument, which I will provide next time. So so this is Genselian, but not strictly Genselian. And another example is this type of X. Strictly Genselian. So Genselian rings, they kind of sit in between local rings. Every Genselian ring is a strictly Genselian ring. Any Genselian ring is a local ring, but it's every complete ring, local ring, is Genselian, but there are more sort of Genselian rings. So this construction here gives many examples. So let's for the last example, let's take for X spec Z. So here I have a point, geometric point, spec FP bar. That will be my X bar. So what is this? What this construction gives? Explicitly. What is the Henselization of Z at this point? So what we are supposed to do here, we are supposed to, for any extension, for any scheme over spec Z, which is a tal, together with a lift, right? We are supposed to give a function on U. What do we get?
Like Q bar intersects this maximal or defined extension.
Very good. So Q bar intersected with weight vectors. Yeah, B bar. Quite a complicated object, and it sits inside Q B bar.
Is it not true that we just add all roots to the medium order right B? That's it?
So why? No, we not at all.
Not simple to identify this
why it's, but there are many even just periodic integers, right, which are algebraic over Q. In particular, it contains just Q bar intersected with ZP. This is enormous, right? There are many periodic integers which are algebraic over Q. Okay, so next time we will study some kind of, this class of rings play the same role again as local rings in classical, in the Zariski topology. For schemes with the Zariski topology, we will study some of its properties. And in particular, well, we need to check that this is indeed an example of a Henselian ring, which is not hard. Okay, I'll stop here. Questions?
Yes, so today we had a corollary that describes H1 et al. Of Z mod n, and if you can restate it in terms of function field of x, I guess we described all unramified abelian extension of a function field of exponent less than n. So
Why exponent less than n?
with Galois group.
Abelian Galois group.
Yeah, all abelian unramified extension of the function field.
This cyclic Galois group.
Okay, this cyclic Galois group of order. Okay.
Say, let's
So
see.
I want to ask whether, like, could you just phrase all of class field theory, at least in the function field case, or is it just follows from homology? Is this possible?
It is. That's a very good question. So, so what is a class field theory? It's the assertion that homomorphism from the fundamental group to Z mod and Z, or to any abelian group, but let's say Z mod and Z, is the same as homomorphism from the Picard group of X, where X is a curve, to the same. It's this assertion. Pick pi1 of X homomorphisms to Z mod and Z is the same as homomorphisms from Picard X to Z mod and Z. All right? That's the one of the formulation of the class field theory. So class field theory is precisely this, where Z mod and Z is replaced by any abelian group, finite abelian group. But, well, any finite abelian group is sum of all this. So that's this assertion. And it seems that that's not what we proved. We proved that we just discussed that. Well, so here X in this formulation, X is a curve, any smooth curve over F Q, not over algebraically closed field, over FQ. And this is class field. And that's not immediately related to what we just discussed, right? First of all, we discussed curves over an algebraic closure of this field. And then instead of taking homomorphism from the Picard group of X to Z mod and Z, we take n torsion points. This seems completely different. Well, again, but here you have the Picard group of X, not of the Picard group of X over K over algebraic closure, right? So if you consider the Picard group of X lifted to the algebraic closure of this field, then this group is very simple. Namely, you have the peak 0, which is divisible group. So there are no homomorphisms from a divisible group to Z mod and Z. And the remaining part is just Z. So you get Z mod and Z. So it's, this group would be trivial, where X is a curve over FQ bar. But indeed, there is a relation. The relation uses either what's called Lenk isogeny or the Veil pairing that you referred. I will say something on this in homework from this.
Also, I mean, it seems that nothing prevents us from just setting x equals spec OK in this exact sequence and obtain, classify all abelian and ramified covers of a number of fields just immediately. Does it?
Well, let's see. So, no, I don't think that we get anything new compared to Kummer theory.
Yes, I guess that's if mu n is contained,
Right,
then it's Kummer theory.
The n of 1.
Not
Yeah. So class field theory is indeed related to the Weyl pairing on n torsion points over an algebraically closed field. And this you can reinterpret things like Artin pairing in terms of a special case of the Weyl pairing on torsion points. So it's Poincare duality. So class field theory is related to the Poincare duality on X for a type homology. More questions? So I think that kind of the most a tricky part of the discussion that we had today is the section of the Galois group, and I really, since this plays a crucial role in everything that will follow, I suggest to kind of see how it works. For example, take the sheaf mu n over spec z and compute the stocks and geometric points of spec z. It's not just given by FP bar points, and can see how the Galois group acts on the stocks.